We want to continue our discussion of Chapter 2 on sets by covering Section 2.3 on set operations. The intersection of two sets A and B, written as you see on the screen with the arch shape or upside down U shape between the sets A and B. That's the symbol for intersection. The intersection of two sets A and B is the set of elements common to both sets A and B. Using Venn diagrams, you can illustrate the intersection by looking at the overlapping areas of the circles that represent A and B. So the intersection is the overlapping part, the elements that are in common to both sets. The union of two sets A and B, written as you see on the screen, which is the arch turned upside down, sort of a U shape, A union B, is the set of elements that are members of either A or B or both. They can be members of A, they can be members of B, or they can be both, but they don't have to be both. That's the union of two sets. Looking at it with a Venn diagram, the union is everything in either A or B or both. For example, use the given sets. A is a set consisting of the numbers 1, 3, 5, and 7, and B is a set consisting of the numbers 3, 4, 5, and 6 to find A union B and A intersect B. We can do it with the Venn diagram just to see it more visually, but you don't have to have the Venn diagram to do these problems. I want to illustrate it with a Venn diagram just to show you the visual representation of it. A is a set containing the elements 1, 3, 5, and 7. B is the set containing the elements 3, 4, 5, and 6. And notice that 3 and 5 are in both sets, so I put them in the intersection of A and B in the overlapping area between the circles A and B. So if I want to find A union B, I'm looking at what's in A or B or both. So that just throws in anything that was in either one gets tossed in to the union. So the union of A and B is a set containing 1, 3, 4, 5, 6, and 7. Now the intersection are the elements that are in common to both sets, and if you look at it in a Venn diagram, that's in the overlapping area, what I sometimes call a football shape, that represents the intersection of A and B. So the intersection of A and B is a set containing 3 and 5. Two sets are disjoint if their intersection is the empty set. In other words, if there is no overlap, then there is nothing in common between the two sets, so the intersection is empty. And two sets are said to be disjoint if their intersection is the empty set. Looking at it on the Venn diagram, there is no overlap. And symbolically, you can say A intersects C is the empty set if the sets are disjoint. Take this example. If A is a set containing 1, 3, 5, and 7, and C is a set containing 2, 4, 6, and 8, find A intersects C. Well, again, if I choose to use the Venn diagram, A is a set containing 1, 3, 5, and 7. C is a set containing 2, 4, 6, and 8. Notice there are no elements in common between those two, so those two sets are disjoint, and the intersection is the empty set. In mathematical problems that involve sets, the word "and" typically means intersection. For instance, the phrase "the elements of A and B" means the elements of A intersect B. Similarly, the word "or" typically means union. The phrase "the elements of A or B" means the elements of A union B. For example, write a sentence that describes these sets. Notice the parentheses. You have to work with order of operations. The parentheses says to do the intersection first. So you're going to intersect B and C at some point. The union symbol means "or." The intersection symbol means "and." So we would read this: the set of all elements that are in A or are in B and C. Now, we're using the comma as a substitute for the parentheses. In the symbolic way of writing it, we'll use parentheses for grouping, but when we're saying it or writing it as an English sentence, we'll put a comma where the parentheses would begin. So in this sense, A is by itself on the left side of the comma. Everything on the right side of the comma is grouped together, which tells you when you're writing it symbolically to put the B and C in parentheses. So this is just something you'll get used to in this course, that the comma, when we're writing out an English sentence, takes the place of the parentheses when we're doing mathematical notation. So watch for the parenthesis in the mathematical writing of it and translate that into a comma. And when you see a comma in an English sentence, when you're going backwards and writing the symbolic version, you'll be using parentheses with everything on one side of the comma in parentheses, if there is more than one thing. On the left side, A is by itself, so you don't need parentheses. So you'll practice this throughout the semester and get used to using that comma as a grouping symbol. And again, just for emphasis, when you see the comma, you know if there's more than one thing on either the left or right of that comma, there are going to be parentheses involved when you go back and write it symbolically. Conversely, when you see the parentheses in the symbolic way of writing it, when you write it as a sentence, you're going to have a comma just before you start your parentheses. Might take a little getting used to, but it's not difficult. We're simply using that comma as a grouping symbol. How about this? J intersect K complement. So we're intersecting J with the things that are not in K. And is intersection. So you'd read this, the set of all elements that are in J and are not in K. So we're simply practicing saying and writing these mathematical statements in common English. Venn diagrams, as I've said before, are useful, and one thing you can use them for is to decide whether certain expressions involving sets are equal to each other. For instance, let's decide where this expression, the union of A, B, complement, in other words, the complement of the union of A and B, is the same as the intersection of the complement of A with the complement of B. And Venn diagrams are perfect for doing that. Let's start with the first one. It's the complement of the union of A and B. I would start off drawing the union of A and B because that's easy. It's just the area inside of either or both circles. The complement, though, is everything that's not inside the area represented by the union. So the complement of A union B is the area outside of both circles. Now move over to the other one and look at it. I want to do an equivalent picture of this. I'm intersecting the elements that are not in A with the elements that are not in B. So if you think about this, A complement, I'm using a horizontal series of lines to illustrate A complement. It's everything outside of A. B complement, I'm using vertical lines. Everything outside of B is B complement. Intersection means and it means overlap. So the intersection of those two sets are the areas that are cross-hatched both horizontally and vertically. And if you look closely, you can see that that area that I've sort of shaded in gray is the area that got cross-hatched. In other words, has horizontal and vertical lines. And if you look at those two things, you can get rid of all the lines I drew earlier and see that the shading on the left and the shading on the right are the same, which means those two statements are equal to each other. If the shading is any different at all, then the statements are not equal to each other. This equality that we just verified is the first of two of what we call De Morgan's laws. The second one I will not derive here, but both may prove useful. One shows you how to rewrite the complement of the union of two sets, and the other shows you how to rewrite the intersection complement for two sets. So the complement of A union B, which we just showed, is A complement intersect B complement, and the other one, the complement of A intersect B, is A complement union B complement. So when you're complementing a union, you end up with the intersection of the two complements, and when you're complementing an intersection, you end up with the union of the two complements. Simple enough. We may have use of those later. Unions and intersections can be done with more than two sets. We will see three sets done quite often. In the case of multiple set operations in one problem, always do the parentheses first and then move outward. So if you're considering the set A, which consists of the letters S, O, L, A, C, E, the set B consisting of the letters L, E, C, T, U, R, N, and the set C consisting of the letters M, L, S, E, R, Y, that's an L, not an I. Perhaps we want to find the union of A with the intersection of B and C. There's no necessarily single way to get started, but since A is sitting right there on the left, I might go ahead and just put in the set SOLACE for that. And then you might go over and look on the right side of the union symbol, and you see that B intersects C. B intersects C means the elements that are in common to B and C. So if you look back up at B and C, you can see that they both have the L in it, they both have the E, and they both have the R, and that's it. So the intersection of B and C, you can sort of look back up and see that pretty easily. So you can see that the intersection of B and C is the set containing LER. Now you're ready to take the union of that set with the set A, and that means you just take everything. If it's in A, you list it. If it's in B intersects C, you list it. If it's in both, you list it. So you just list every single letter you see down there on the bottom line. And if you look, there's an S, there's an O, there's an L, there's an A, there's a C, there's an E, and there's an R. So the union of A with the intersection of B and C consists of the set containing the letters SOLACER. You could do that with Venn diagrams, but as I said earlier, you can do these problems mostly without Venn diagrams, although Venn diagrams can be useful as a visual aid. How about this one? We want to find the intersection of the union in A and B with C. So this time you might say, well, okay, I start off with A union B. That means everything in A or B or both. So if it's in A or B or both, I just throw all the letters into one set. You don't list one letter twice, even if it appears twice, but you put every letter that appears in either set in the resulting set. So A union B, there's an S, there's an O, there's an L, there's an A, there's a C, there's an E in A. And then when you look over at B, you've already listed some of the letters, but you do have some extra letters that weren't listed earlier, in particular a T, a U, an R, and an N. So A union B is the set containing SOLACETURN. Now on the other side of the intersection symbol you have C, and because we're getting way down on the slide, I'll just relist what C is from up high. C is the set containing MLSERI, and now I'm doing intersection. Intersection means overlap, which means the elements are in common. If you look through there, both have an S, both have an L, both have an E, both have an R, so the intersection is the set containing S, L, E, and R. And there you go. This is not difficult, but you do need to be careful, and you need to pay attention to the grouping symbols. Venn diagrams can also be drawn to represent the relationships between three sets instead of just always two sets. Once you get beyond three sets, Venn diagrams are not very helpful. But for two or three sets, Venn diagrams are very useful. So if you have three sets, you have to write them this way so that you have the overlapping areas between each pair, plus you have an overlapping area for where all three circles intersect. So if I wanted to shade the intersection of A and B, I would have that, what I sometimes call a football-shaped area that represents the overlap between A and B. If I wanted to shade the intersection of A and C, I would have that, again, that football shape that represents the overlap between A and C. And if I wanted to shade B intersects C, I would take the overlapping region between the sets B and C, and that would be B intersects C. What about A intersect B intersect C? Those are the elements that are common to all three, and you can just see this without doing anything, that the overlapping area for all three sets is that sort of pie shape where all three circles intersect. So that's A intersect B intersect C. How about this? A intersect B complement. Intersect means overlap. So first of all, I might say, in my mind, just read it to myself or say it to myself, this represents the elements that are in A, but at the same time not in B. So it's inside of circle A, but outside of circle B. And if you just say it to yourself that way, you can picture the solution set without really doing any intermediate work. The elements that are in A, but at the same time, they're not in B. And the missing part is the part that would overlap into the circle B. I want to mention this just because I think it's important to know it exists. We're not doing much formally with all these properties of sets, but just like properties in algebra with commutativity and associativity and distributivity, we can do the same thing with sets. I just wanted to show you that those things exist. We really don't have much use for them in what we're doing, but they're important if you do more involved things with sets. Let's look at this example. It's very interesting. It's an application of additive color mixing. Just as a background, computers and TVs use additive color mixing, and this set of three circles forming a Venn diagram shows us when the primary colors, which are red, green, and blue, are mixed together, they give you a white. If you look at set notation to describe that, you would say that R intersect B intersect G is white. In other words, red and blue and green is white. Yellow, cyan, and magenta are called secondary colors, and a secondary color is produced by mixing exactly two of the primary colors. Now, you don't have to be an expert in this, but that's the background you need to know to answer this actually relatively easy question. Which color is represented by R intersect G intersect B complement? We know R intersect B intersect G is white, but what is R intersect G intersect B complement? So I would start out by just looking at R intersect G. In other words, where red intersects G, where the red circle intersects the G circle. We're going to use R for red, G for green, and B for blue, and we're assuming that we're using this additive color mixing. With all that in mind, R intersect G is where the red circle overlaps the green circle, and you can see that I've indicated it on the Venn diagram. It's what I usually call a football shape. But then we also want it to not be in the blue circle. B complement means it's not in the blue circle. So we're looking at that football shape region, but only the part of it that's not in the blue circle. And as you can see, if it's not in the blue circle, but it's in that football-shaped region, then it must be yellow. And the answer is yellow. So this type of analysis is very easy to do if you understand what you're trying to do, and it's a perfect application of Venn diagrams. Here's a really important application of Venn diagrams. It has to do with doing blood groups and blood types. Karl Landsteiner won a Nobel Prize in 1930 for discovering the 4 different human blood groups. He discovered that the blood of each individual contains exactly one of the following combinations of antigens. If you have only A antigens, you're called blood group A. Venn diagram-wise, that would be shading the part of circle A that doesn't overlap into circle B. If you have only B antigens, you're said to be in blood group B, and you'd illustrate that on the Venn diagram by shading the circle B, but not bleeding over into circle A at all. Or you could have both A and B antigens. That would be blood group AB. And if you have A and B, that would be the intersection. That would be the football-shaped region where A and B intersect. Or you could have no A antigens and no B antigens, and that's called blood group O. And type O is the area outside of both of the circles. In other words, you're shading things that aren't in either circle. That's blood group O. So Venn diagrams are very useful for doing this. In 1941, Landsteiner and Alexander Wiener discovered that human blood may or may not have something called an Rh factor. Blood with this factor is called Rh positive, and you denote it by the letters Rh with a plus sign. Once the Rh factor was discovered, the Venn diagram goes from having 2 sets A and B to having 3 sets A, B, and then a circle for the Rh positive factor for having the Rh factor. That's Rh positive. So we throw in an Rh plus circle. It makes it more complicated, but it does explain how the Rh factor fits in with the blood types. This diagram makes it clear that there are 8 different blood types. If you look at the Venn diagram, you can see where all of those lie, and we're going to go into more detail with that in a moment. The point is, this Venn diagram illustrates the 8 blood types considering the A antigens, the B antigens, and the Rh factor. It breaks it up into 8 blood types. Anything that's inside the Rh positive circle is going to have a plus. Anything that's not inside of the Rh circle will have a minus. So when you're assigning pluses and minuses, anything that has a presence inside of the Rh plus circle is going to have a plus. Everything else has a minus. Let's show how simple this really is. Let's take these 4 people, Roberto, Sue, Alex, and Lisa, and the arrow points at where they lie in terms of these 8 types. And let's see if we can classify them. Let's start off with remembering what everything means. Type O happens if you're not inside either A or B. Type AB happens if you're in the intersection of circles A and B. There's a plus if you're inside the Rh plus circle. There's a minus if you're outside the Rh plus circle. With that information, we should be able to classify all 4 of those people. So let's start off with Alex. Alex is inside of the A circle, and Alex is also inside the Rh positive circle. That means Alex is A positive. Lisa is not inside of either A or B, so Lisa must be an O. but Lisa is inside the RH positive circle, so Lisa must be O positive. Sue is inside the A circle, but not in the overlap. But Sue is not in the RH positive circle, so Sue is a negative. Sue would be A negative. And finally, Roberto is in the overlap between A and B, so Roberto is an AB, but Roberto is not inside the RH positive circle, so Roberto would be an AB negative. So you can see how easily this works once you remember those four things in the remember column. Okay, let's end up with a sort of a fun problem. Look at this. It says which Venn diagram places each element below in the correct region, and you've got four possible answers, only one of which is correct. You start off with a universal set. It has several people's names: Sue, Bob, Al, Joe, Ann, Herb, Eric, Mike, and Sal. And then you've got three additional sets. You've got the set called A, which consists only of Sue and Herb. You've got the set B consisting of Sue, Eric, Joe, and Ann. And then you've got the RH positive set consisting of Eric, Sal, Al, and Herb. And the question is, which one of those four possibilities is correct for this problem? I would suggest doing it by elimination. I would start off, looking for things in the universal set that are in all three sets, A, B, and RH positive. And if you look through there, you'll see that there's nothing common to A, B, and RH positive. Sue is in A and B, but not in RH positive. Eric's in RH positive and B, but not in A, and so on. There's nothing. So that gives you a big clue right away. The correct solution is going to have an empty set at the intersection of all three circles. So if you look at the intersection of all three circles and all four possibilities, you'll see that Sue is in the intersection of all three circles for the first set, the first Venn diagram, and Sue is also in the intersection for all three in the last Venn diagram. Well, that can't be right. We've just said that there's nothing in that intersection. So we've already eliminated two of the four choices. That's why I said this is sort of a fun problem. You can sort of play around with this and figure it out logically. Then I would sort of jump to the other end, I believe. There are other strategies, but I think I would start looking for elements that appear in all three, and then I would jump to the absolute opposite side and look for the elements that appear in none of the three sets. So if you look in the universal set, you've got Sue, Bob, Al, Joe, Ann, Herb, Eric, Mike, and Sal. If you look through there and scan sets A, B, and RH positive, you will see that Bob is not in any of those three sets, and neither is Mike. But everyone else is. You can take some time and look at that and be sure. Sue is in at least one of the sets. So is Al. So is Joe. So is Ann. So is Herb. So is Eric. And so is Sal. So it's only Bob and Mike that's not in any of them. Well, if those two are not in any of them, their names should be outside of all three circles. Looking back at those four choices, Bob and Mike are outside of the circles in the first choice, but we've already eliminated that. That's not even possible. And also in the last choice, but we've already eliminated that as well, so that's not possible. Of the two remaining possibilities, the two choices in the middle, only one of them has just Bob and Mike, and that is the second choice. The third choice also throws in Al, and Al is not correct because Al is in that RH positive set, and we're looking for the names that aren't in any. So as you can see, by a process of elimination, we've already deduced that the answer must be the second choice. Now, if you're working a problem later and doing these two things still leaves you with more than one possibility, you have to keep going. You could continue this process by looking for elements belonging to just one set and just two sets, but we're done because we've already eliminated everything but one possibility, so that remaining possibility must be the 1.